Now let's move on to multi-layer neural network. So we have seen that the perceptron network is a linear classifier, which means perceptron network can solve linear problems only. But vast majority of real-world problems are nonlinear problems. So that means there are very few problems we can solve with by using perceptron network. So because of all these problems, this area of neural network, including perceptron, has been actually forgotten for many years up until this multi-layer neural network is introduced back in 1986. So the question now is, how do you solve nonlinear problems using neural net? Yeah, as I said, the single layer perceptron solves linear problems only. Okay, so the question is, how do you solve nonlinear problems using a neural net? Because almost every problems in real world is nonlinear problems. So actually, there are two solutions to these questions. So the first one is we add hidden layers in perceptron, which makes multi-layer neural network. So if you look down here, in this neural net, we have input layer, we have output layer, and in between these two, we have another layer called the hidden layer. And every hidden node is connected to every input node is connected to every hidden node. And again, every hidden node is connected to every output node. Okay, so that's the structure of this multi-layer neural net. So that's the first solution here. We add a hidden layer in between input layer and output layer. But actually, you can add multiple hidden layers in between input layer and output layer. In this picture, it shows only one hidden layer, but you can add as many hidden layers as you want. Second solution to this question is for each of these nodes, it contains activation functions. If you remember the structure of the element in neural net, it contains activation function, right? And also in perceptron, as for activation function, it uses either a step function or a linear function. But in this multi-layer neural net, we use non-linear activation function such as sigmoid function. So for this particular questions, how do you solve nonlinear problems using a neural net? So the answer we have here is there are two answers actually. The first one is we add hidden layer, okay, and the second answer is we use nonlinear function such as sigmoid function, okay, as an activation function for each of these nodes, okay. So by using these two solutions, okay, then this multi-layer network now becomes non-linear classifier. That means now this network is able to solve non-linear problem. Okay, so that's what's gonna study in this chapter. So this multi-layer network is the most widely known neural network architecture. And actually, the deep learning is actually very similar to this neural network structure. And in terms of the network structure, deep learning is actually a neural network with many hidden layers. Okay, that's the main difference between the neural net and the deep learning structure. Okay, now let's train the multi-layer network. The training algorithm for a multi-layer network is called a backpropagation algorithm. And by using this backpropagation algorithm in a multi-layer network, finally our neural net becomes a non-linear classifier. So it is now a non-linear classifier, and that means it is now capable of learning a variety of non-linear decision surfaces. So this backpropagation and multilinear network is the first major breakthrough in neural net research area, and it was proposed by this three-person back in 1986. Actually, the second author, Jeffrey Hinton, he made another major breakthrough in neural net in 2006, and it is called deep learning. So he is now called the father of deep learning. So anyway, let's take a look at what the backpropagation algorithm is and how it works. So backpropagation algorithm is again is a training algorithm in a multi-layer neural net, and it is one of the most famous algorithm in neural net, and it is based on a gradient descent method. And as I said, many machine learning algorithms are based on gradient descent method, and backpropagation is no exception. So in backpropagation, so as I said in a previous slide, it uses a different activation function. Actually, in the original model, it uses sigmoid function as an activation function. So backpropagation uses non-linear activation function such as sigmoid. So if you remember, in perceptron training rule, the activation function we use was a step function. And the problem of a step function is it is not differentiable, it is not continuous, it is not differentiable. So we cannot use gradient descent, okay, in a perceptron training rule. So that is the problem. So in order to use gradient descent in delta rule, this activation function has changed to a linear function. Okay, so now it is continuous and differentiable. But this linear function is linear function. Okay, so it is non-linear. So still the entire perceptron network is linear classifier. Okay, so still produces only linear function. By the way, I'm going to add one thing here. So even though you add multiple layers, multiple hidden layers, okay, and then if all the activation functions are linear functions, then the entire network is still linear classifier. Okay, so even though there are many hidden layers, if the activation function is a linear function, entire network is linear classifier. Okay. So in backpropagation, we use nonlinear function such as sigmoid function. Okay, so in backpropagation, we use sigmoid function as the activation function. So the key is sigmoid function is continuous function. It's differentiable. So we are able to use gradient descent, and this function is non-linear. That means entire network is now non-linear classifier. Okay, so the backpropagation algorithm uses sigmoid function as the activation function. So here, let's talk about the sigmoid function, what it is and how it works in neural net. If you remember, this is the picture of one node or one computing element in neural net, and it takes some input here, and each input has its corresponding weight. and then we do each input is multiplied by its weight, and we do summation here, okay, like this. And let's say this summation is called NET, net value. So net value is the summation of multiplication between the weight value and the input value. And then this summation, this net value goes through activation function, okay. So depending on the network structure, we use different activation functions. So if you remember, in a perceptron training rule, for this activation function, we use the step function, okay? And for delta rule, we use the linear line as the activation function. And here in backpropagation algorithm, we use what is called the sigmoid function, which look like this. Okay, so this sigmoid function is the activation function of a backpropagation algorithm. So this summation of this multiplication net value goes through this activation function, and then it becomes the final output of this neuron node or computing element. Okay, that's how it works. So down here, it shows the definition of a sigmoid function. So given a value of x, this is definition of sigmoid function. Okay, and this one here, the shape of this sigmoid function look like this. Okay, so that's a sigmoid function in neural net. So the advantages of using a sigmoid function is the following. First, it is continuous function. As you can see, this is continuous function, and also it's a differentiable. It's differentiable. So because it is a continuous function and differentiable function, we are able to use a gradient descent method in backpropagation algorithm. Okay, because the activation function is continuous and differentiable. Okay, that enables us to use gradient descent in backpropagation. Okay, and another advantage of sigmoid function is its non-linear activation function. So as you can see here, this activation function, sigmoid function, is not linear. It's curved, right? So linear function means the shape of function is line. Okay, that's the definition of linear function. The definition of nonlinear function is the shape of curve is nonlinear. Okay, so definitely the shape of sigmoid is not linear, not line. Okay, so that means sigmoid function is nonlinear. So as I said in previous slide, using nonlinear activation function is very important because if you use a linear activation function in a multi-layer network, okay, then no matter how many hidden layers you have, the entire network is still linear classifier. Okay, so that's why this using nonlinear activation function is so important. Okay, so sigmoid is nonlinear function, so this makes the entire multi-layer network nonlinear classifier. Okay. Okay, this continues our discussion about sigmoid activation function. This one here is more general definition of sigmoid function. Unlike the definition in the previous slide, it contains k constant here, okay, and actually this k constant determines the degree of steepness in this curve. So if the k value is very high, this curve becomes very steep like this. Okay, and if k value is very small, then it makes this curve very gentle or slow like this. Okay, So that's what this k does in a sigmoid function. So again, this is the shape of a sigmoid function. So it ranges, as you can see here, it ranges between 0 and 1. And if x value goes to minus infinity, its output is very close to 0. And if x is goes to positive infinity, output is close to 1. Okay, so what's the property of sigmoid function? Another interesting property of sigmoid function is, so when we use a sigmoid function as activation function, and when you use a gradient descent method, we have to differentiate the activation function. Okay, so in gradient descent method, we need to differentiate the error function which contains activation function, right? So we have to differentiate the activation function in gradient descent method. So one interesting property of sigmoid function is the derivative of sigmoid function is given as follows. So it's very simple, it's very nice, very clean. Okay, so derivative of sigmoid function is very clean and simple, and this makes the computation of a gradient descent rule very simple, very easy. Okay, so that is a sigmoid activation function, and now we have a multi-layer neural net, and each node has a sigmoid activation function. Now it's time to derive the actual gradient descent rule to train the multi-layer neural network, which uses sigmoid function. Okay, actually that gradient descent rule is called a backpropagation algorithm. Okay, before we move on to backpropagation algorithm, let's digress a little bit about the importance of activation function. So I said it is important to use nonlinear activation function in neural net. Okay, so if you look at this picture here, let's say these are red and these greens are class labels. So we have binary class values. And the goal of classification learning is to find a boundary which separates between red and green. Okay, so we have boundary like this, which separate between these two. Okay, and that is the goal of classification learning, right? But if you use a linear activation function, okay, for your multi-layer network, then it makes the entire network a linear classifier. Okay, then linear classifier means the shape of your classifier, okay, is line, straight line. So this is an example of a linear classifier. So in this example, okay, using this straight line, no way you can find a boundary which separates between red and green. Okay, so that is the problem. That's why we have to choose a nonlinear activation function, okay, in our multi-layer network. If you look down here, this one actually talk about this one here. So if you increase the number of layers and the number of neurons, then it makes your network more complex, and it can actually represent more complex functions. So in this picture here, let's say you have 3 hidden node, okay, then it is able to represent a boundary like this, okay, but still we have some error here, right? And if you increase the number of hidden node up to 6, okay, then it now can represent more complex boundary like this. Okay, this is more complex than this one. So this is the new boundary using 6 hidden node, but still we have some error here. Okay, these errors are resolved, right? So if you increase more, and now we have 20 hidden node, then the boundary looks like this, and we don't have error. Okay, this is the perfect boundary between red and green. So if you increase the number of neuron like this, or if you increase the number of layer, the neural net becomes more complex, which means it can represent more complex functions like this. Okay, that is the advantage of increasing the number of layer or number of neurons. But the problem is, if you increase the number of layer or number of neurons too much, then your network becomes too complex, and it causes overfitting problem. Okay, so if your model is too complex, your neural net is too big, it suffers from overfitting problem. So about the overfitting problem, I talked about this issue in different chapter, so I don't go into detail of this. So anyway, if when you decide the size of a neural net, the complexity of neural net, so you have to draw a line somewhere between, not too complex, not too simple. Okay, so that is the art of learning in neural net. Okay, now let's see how the backpropagation algorithm works. As I said many times, the backpropagation algorithm employs a gradient descent method in order to minimize the error between the network output and the target values. So if you remember, in the gradient descent method, the first step we do is to define error function, right? So backpropagation is based on gradient descent. Okay, so that means the first step we do is to define error function of the network. So this is the definition of error function in backpropagation algorithm. So in this case, we assume there is a multiple output node in the neural net. Okay, in the output layer, we assumed there are multiple output node. Okay, so anyway, so this is definition of error in backpropagation algorithm. So if you look carefully, so this is the error between target value and output of network. Okay, T means target value, O is output of network. Okay, so this is error between target value and network output, and we put square here. The reason we put square here is without square, some error is plus, some error is minus, so they may cancel out each other. Okay, so because of that, we put square here, and then this square is added for every output node. Okay, so K is for every output node. Okay, and then this square value is again added for every data. Okay, DE means for every data. Okay, so this errors square value of error is added for every output node and for every data. Okay, so that's the basic definition of error function in backpropagation algorithm. The reason we put 1/2 here is later on we're going to differentiate this error function. So in that case, if you differentiate these two comes to the front. Okay, so so they cancel each other 2/2. Okay, so for the sake of simplicity, we put 1/2 here. Okay, so Anyway, that is the definition of error function in backpropagation algorithm. Okay. Actually, this error function is used in batch backpropagation. Okay. So, what is batch backpropagation? So, in batch backpropagation, the algorithm read entire data, okay, entire data, and then compute the error, okay, using the entire data, and then we update weight values of network, okay. That's a batch backpropagation. And another version, another backpropagation algorithm is called stochastic backpropagation. So in stochastic backpropagation, it read one data, okay? It read one data and define error function based on one data, and then update weight values using one data, okay? So that's how it works. So in batch backpropagation, you read entire data and then update your weight. And in stochastic backpropagation, you read one data and then update your weight values. Okay, so that is the difference. So here in this in batch backpropagation, this is the error definition, and as you can see, this error function is defined for every data here. Okay, so this error function is used in the batch backpropagation. So as I said, batch backpropagation updates the weights after reading the entire data, the batch of data. That's why it is called batch backpropagation algorithm. The next backpropagation algorithm is stochastic backpropagation algorithm. So as I said, in stochastic backpropagation algorithm, it read just one data, okay, and then update weight values of network. Okay, in batch backpropagation, on the other hand, it read entire data and update weight values in the network. Okay, so that is difference. So this is the error function in stochastic backpropagation algorithm. So if you compare this with the error function in the batch backpropagation, the only difference is there is no summation over data D. Okay, that's the only difference. So that means you read one data, you read a specific data D. Okay, then using that particular data, we define error function, error value like this. Okay, so that's the main difference. So for every data, you define error. Okay, and then you update weights. So error function is defined per every sample, every data, and then we update weight values after reading each sample. Okay, so that's the how the stochastic version of backpropagation works. So stochastic backpropagation is faster than batch backpropagation. It is clear because in stochastic version, we do not have a summation of entire data, okay, which makes stochastic backpropagation much faster than batch version, right? Because there is no summation here, right? But the problem of a stochastic backpropagation is sometimes it may oscillate with high variance. So oscillate means, so in stochastic backpropagation, okay, sometimes this error is very big, okay, and sometimes this error is very small, depending on this data. Okay, there are many data. Okay, so depending on the data, sometimes we have very high value of error, sometimes we have very low value of error, right? So, so what happened in stochastic backpropagation is in batch backpropagation, the algorithm, backpropagation algorithm slowly but gradually move toward the goal, okay, goal of learning. But in stochastic backpropagation, because this error value is sometimes very high, sometimes very low, okay, its variance is very high, okay, then what happened is this algorithm actually sometimes just wandering around, just moving around, okay, with just pointlessly, okay. Instead of going toward a certain goal, it just wandering around, okay. So that's what happens in stochastic backpropagation, okay. So there is pros and cons, okay. This algorithm is faster than a batch version, but sometimes it oscillates, okay, and instead of going toward, okay, toward the goal, gradually, it's just moving around. Okay, so that's the problem of stochastic backpropagation. So in many cases, so sometimes people combine these two and use what is called mini batch backpropagation. So in mini batch backpropagation, it is kind of compromise between these two versions. Okay, so instead of reading entire data or single data, we read n. Okay, a batch size of n data. Okay, like let's say n is 100, then the algorithm read 100 data. Okay, and then read update weight. Okay, then it read the next 100 data and then update weight. Okay, so that's how it works in a mini batch backpropagation algorithm. So actually these days, this mini batch backpropagation is the most popular version of backpropagation. Okay. In this chapter, we focus on the stochastic backpropagation algorithm. Okay, I'm going to explain the mechanism of stochastic backpropagation algorithm here in this chapter because it's much easier to explain. So in this chapter, we study the stochastic version of backpropagation algorithm. So the pseudocode of stochastic backpropagation algorithm is given in the next slide. It actually consists of two phases. The first phase is a forward phase, where algorithm moves from input to output. And the second phase is a backward phase, where it moves from output to input. So as for notation, x sub ji means this is input from node I to j. Notice this notation is reversed. Okay, xji means this is input from node I to j. Okay, and similarly, w sub ji means its weight values from node I to node j. So this wji is weight value for input xji. So as I said earlier, stochastic backpropagation is based on gradient descent, and that means the first step we do is to define error function. So this is the error function for stochastic backpropagation. Okay, and again, because this is stochastic, there is no summation over data here. Okay, so this is stochastic version. So in a gradient descent, once you define a gradient, once you define the error function, then now you can update your parameter w by using this formula. Okay, that's how the gradient descent works. You define your error function, then you update your parameter, in this case w. You can update your weight values by using this formula. Okay, so current value plus delta w ji is new value. Okay, and the delta w ji is minus eta, which is constant, times the derivative of error function with respect to wji. Okay, so finally if you compute the value of this derivative, then we are able to update our weight values by using this formula. Okay, so the remaining homework we have is how to compute this derivative of error function with respect to Wji. Okay. This slide shows the pseudocode of a backpropagation algorithm. Again, this is a stochastic version. So in the beginning, we initialize all weight values in the network like this. All weight values to small or random numbers. Okay. So in the beginning, we have no idea what these weight values are. So you initialize with small numbers. Then until satisfied, we repeat this. Okay, and this procedure is repeated until satisfied. So until satisfied means you can determine certain terminal conditions. Okay, so for example, this iteration can be executed like maybe 100 times or something, or you can define a threshold of error, saying the size of error is less than this threshold, then the program stops. Okay, things like that. So you can define your own terminal condition. So until the terminal condition is satisfied, you repeat this. So you for each training example, so you read one data. So again, this is a stochastic version. For each training example, you do this. So the first phase is a forward phase. In the forward phase, the network read the input, okay, and input is propagated to the next layer, hidden layer, and then is propagated to next layer, which is now output layer. Okay, so input is propagated from input layer to the output layer. Okay, that's forward phase. And in each layer, you compute the output of node. Okay, and also this output is forwarded to the next layer. That's what's happening in forward phase. In the second phase, it is called backward phase. In the backward phase, so now you compute the as a result of forward phase. Now the network has output. Okay, now we have network outputs like this. So by using this output, now you can compute the error. Okay, error of the network. Okay, so now you compute error, and then this error is propagated backward from output layer to input layer. Okay, that's what's happening here. And along the way, we update all these weight values. Okay, that's what we do here in backward phase. So in step 2, for each output node K, so we have, in this case, we have 3 output nodes. So for each output node K, we compute this. Delta K is OK means output of K node, okay? Output of K times 1 minus OK times T is the target value of this data, okay? Target value minus output of the K node. Okay, so this is the definition of delta K for this output node K. So for every output node K, we compute its delta value K, delta K. And then we move on to next layer, which is the hidden layer. So every hidden node H, for every hidden node H, we compute delta H, which is equal to output of node H. Okay, OH means output of node H times 1 minus output H times this one here is, let's say you're gonna compute the delta value of a certain hidden node, let's say this one. You're gonna compute the delta value, delta H, okay, for this node H, hidden node H. Then this means, okay, this one is connected to a 3 output node here, right? This is connected to this output node, and this output node, right? So this delta K is defined here. For every output node, we have delta K. So delta K is multiplied with WKH. So for this output node, we compute delta K, and it is multiplied by weight value of this one. Okay, that's what's happening here. For this output node, we compute the delta value of this output node, and it is multiplied with W value here. Okay, and again, this delta value, okay, is multiplied by this weight value here. Okay, that's what's happening here. So every delta value of output node is multiplied by weight value, its corresponding weight value, and we do summation here. Okay, and the summation is multiplied with this one. Okay, so that is the definition of delta value for hidden node. So remember, depending on whether the node is output node or hidden node, we have different delta value. Okay, this is the delta value for output node, and this is delta value for hidden node. Okay, now we're going to update the network weight. Okay, network has many weight values. Now we're going to update these weight values. So for every weight in the network, this is the formula from gradient descent. Again, backpropagation is using gradient descent. So this is the formula from gradient descent. So current weight value plus delta Wji is new weight value. Okay, and the Wji is learning rate eta times delta J times xji is input, which is given here. Okay, so that's definition of delta Ji. One thing you have to remember here is in the previous slide, in the notation of the pseudocode, this xwji is weight value from node I to node J. You notice the index is reversed. Okay, this weight value wji is weight from node I to node J. Okay, not from node J to node I. Okay. So again, this is the same. This is input value from node I to node J. Okay. So finally, this is a current value of W, and this delta is added by a delta Wji, and Wji is learning rate, which is constant, times delta times x input. X input is given here. So the only thing what matter here is delta J. So for example, you want to update this weight value here. Okay, so you want to update this weight. Okay, so this weight current value is this, and let's compute the delta Wji. Okay, so this one is Wji. Then the delta Wji is a learning rate, whatever constant, times input is given. Okay, so what is this? Then you see that this delta J, the first index. Okay, and remember this W is a weight from node I to node J. So when you update these weight values, for this delta, you use the delta value of this one. Okay, the first index. Okay, so you want to update the weight value of this one for this one, for this delta, you use the delta value of this one. Same thing, if you want to update the weight value of this one, okay, then you're gonna use it for this delta value, you're gonna use delta value for this node, okay. Let's say you're gonna update the weight value of this one, then for this delta J, you're gonna use delta value for this node, okay. So always use delta value of to part, not from part. Okay, that's the key point here. So by doing so, we are able to compute the the delta value, and now we can update the W value by using this formula. So that's the basic structure of backpropagation algorithm. And next slide, I'm gonna explain how these formulas are derived. Okay. So this slide explains the pseudocode of the next slide. Okay, and so in step 1, it propagates the input toward the output layer. Okay, that's the step 1. And then in step 2, 3, and 4, we compute the error. Okay, error of the network, and the error is propagated to input layer, and along the way in each layer we update the weight values. Okay, that's what's happening in step 2, 3, and 4. Okay, so this algorithm actually repeats for every data. It repeats the process, the forward process and backward process. And the entire process is repeated many times. Okay, so backpropagation repeatedly iterates over the training examples, and again for each training data it computes output and also computes the error of the data. Now compute the gradient with respect to the error of the example, and then using this gradient we update weights in the network. And also this update process is iterated until the terminal condition is met. So as for terminal conditions, you can define your own terminal conditions. There are some examples here. A variety of terminal conditions can be used to stop the algorithm. Maybe in the first case, you give a fixed number of iterations. So for example, I'm going to run this algorithm like 1,000 times or something, okay? Then algorithm iterates this procedure 1,000 times and stops, okay? Or you can define some threshold there, and if the size of error, okay, is less than this threshold, then the algorithm stops there. Okay, that's the second case. Or you can define a separate validation data set. Okay, and by using this validation data set, if the error on the validation data set is less than a certain threshold, then you can stop there. Okay, so you can define many terminal conditions on your own, including conditions here. Okay. So in the pseudocode of backpropagation algorithm, you can see a number of the weight update rules. Okay, so in this slide, we're gonna explain how these weight updates rules are derived by using gradient descent method. Again, backpropagation is based on a gradient descent method. So in this slide, we're going to explain the weight update rule for output unit weights first. Okay, output unit means, suppose this is output node, then there are weight values which connects from a hidden node to output node. Okay, so this slide is for updating these weight. Okay, which connects to output node. Okay, the weight update rules for hidden node will be explained in the next slide. Okay, this slide is about updating these weight values which connects to output node. Okay. So again, this is kind of definition of a gradient descent method. Okay, gradient descent weight update rule. So all the value and the delta wi, and delta wi is like this. This is constant. So again, our goal is how to compute this the derivative of error function. Okay. And this is, as a reminder, this is a structure of a single node. Okay, as you can see, we have input and weight values, and the summation of this multiplication is called net. You're gonna call it net. This is summation of input times weight values. Okay, this net will be used here, and then net value is again used in sigmoid function. And then the output is the sigmoid output is the output of the node. Okay, so that's the structure of one single node. Okay, so again you're gonna compute the weight values which connects from hidden node to output node. Okay, so okay, the goal here is how to compute this. Okay, the derivative of error with respect to W is kind of, you can assume this is kind of the effect of W on error function E. Okay, roughly speaking, you can assume this derivative is kind of the effect of Wji on error function E. Okay, so anyway, so this one here is, so you're gonna compute the effect of a certain weight value W, okay, with respect to error function down here, okay. But you have to go through this weight value, go through net, it goes through a sigmoid function and go through error function, right? So it has to go through many steps to reach the error function, okay. So in here, in the first step, this derivative of error function in terms of W actually consists of two parts. The Wji, this weight, goes through net first, okay, and then this net value, okay, affects error function, right? That's the first step. So Wji affects net value first, and then this net value affects error function, right? So because of chain rule, this one original derivative is this times this, right? This is true. This is because of our chain rule. Okay, then this part is easy. Okay, if you look at the definition of net, derivative of net with respect to x is very simple. With respect to W is very simple. Okay, it's this is xji. So this is super easy. So original derivative form is this times this, and this is now xji. This is easy. Okay, now let's compute this part. Okay, this is the effect of net, okay, on error function. But net has to go through the activation output function first, right? Activation function first. Net goes through output function, and then output function affects error function, right? So again, this is decomposed into these two parts. Net affects output first, and then output affects error function, right? So this is decomposed into these two parts, right? And then this one here is, this is derivative of activation, which in this case sigmoid. Okay, derivative of sigmoid function in terms of net. Okay, this is this. In a few slides back, when I explained the property of sigmoid function, then the one of the interesting property of sigmoid function is its derivative form is like this. Okay, its derivative form is very simple and very clear like this. Okay, that's one interesting property, one advantage of using a sigmoid. So this one, because of that, this is this. Okay, derivative of this sigmoid function is this. So this is done. And this is final homework. Okay, this one here is the derivative of error with respect to output, right? So if you look at the definition of error like this is definition of error. Okay, then you differentiate with respect to O, right? With respect to O, then which becomes this. Okay, then we are done. This one is this. Okay, and this one is this, and this one is this. Okay, so by the way, this t is the target value, O is the output, and again x is input. And this picture shows, so I said this slide explains the weight update for output node. Okay, so now we are updating this weight, which connects from hidden node to output node. Okay, so finally this delta wji is minus eta times this derivative. Okay, and this derivative now is this times this times this, right? So all together, put this all together, delta wji is nt minus o times o1 minus o times x, okay, which is described in pseudocode of backpropagation algorithm. So this was the derivation of weight update rule for output node. In next slide, we're going to show how these weight update rule for hidden nodes are derived. So in previous slide, we have seen the derivation of weight update rules for output unit weights. This one is about the derivation of weight update rules for hidden unit weights. So the main difference is in the previous slide, the weight is connected directly to output node, but in this case, this node, you want to update this weight value, then it has at least one more layer of node between this node and the output node. Okay, so that means when you want to update this weight, then that does not influence the error of network directly. Okay, it actually influences this node first. Okay, and then this node, after that, this node influence this output and error of network. Okay, so this network weight value actually indirectly influence the error of network through these node, right? So that's the main difference. Okay, so let me begin with the downstream J. So let's say this node is J. You want to update this weight Ji. Downstream J is these are node, okay, whose input is the output of J. Okay, so output of J is connected to the node in downstream J. Okay, this J is connected to every node here, and these are called downstream J. Okay, so when a node J is an internal or hidden node, we define downstream J, which is this one, to all nodes whose inputs include the output of J. Okay, so as a result, this WJI weight influences the network indirectly through output and hence error. Okay, and this net J Net J is the net value within the node J, influence the network output only through the node in downstream. So when you update this, you want to update the output of J, but that output of J indirectly influence the network output and also influence indirectly the error value of network, right? Okay, so let's get started. Again, we are using gradient descent. This is the basic formula of gradient descent. Okay, W is W plus delta W, and delta W is minus eta times derivative of error with respect to W. Okay, these are same. Again, our goal is how to compute this one. Okay, in this hidden node case. So this one here, this is a kind of, you can assume this is influence of W on error function, okay? Then this can be decomposed into these two parts. This means your weight value, W, okay, influences the net value of J node, right? And then net value of J influences error function, right? Yeah, again, this is from net J, it goes through many other steps, but anyway, your net weight value influences net value first, net value of J node first, and then this net value of J influence error function, right? So this is true. So here, this is easy. This is derivative of net J with respect to Wj. This is super easy. Okay, if you remember the definition of net, this is xji. So this is easy. This is xji. Then now let's compute this part. Okay, this is the influence of net J on error function. Okay, so net J value in the J node actually go through this node. Okay, this influences each of this node. Okay, and then each of this node influence output node, right? That's what happens. So this one actually is decomposed as this. So net J, okay, net J value influences each element, each node in downstream, right? This J is connected to every node in downstream, right? So for every node in downstream J, okay, every node in downstream J, it is decomposed into this is influence of, okay, this is influence of net J on net K. So this net value J influences net K value here. And again, this net J influences another node at net K here, right? So, and then using this net K, this one again influences error function. You can say like, okay, this one influences this, and this one influences this, right? You can roughly speaking, this one says this one influences this, and this one influences this, and also this one also influences this, and this one also influences this. So use the summation of this, okay? So for each node in downstream, okay, net J influence net K, okay, net K, and net K influence error function of network, okay? This one, this is already computed. Okay, this is already computed in previous slide when we compute the when you compute the weight update rule for output unit node. Okay, so we use that result here. And for this one, when you influence, when the net J influences net K, it goes through output function of J node. Okay, you remember in J node, you compute net value of J and then go through activation function. In this case, sigmoid function, right? So net j goes through output function, activation function, and then this activation function influence net k. Okay, so this is decomposed into these two parts. Okay, and this one is again easy. Okay, this is a derivative of net k with respect to oj. This is pretty easy. Okay, and for this one again, this is again the property of sigmoid function. The derivative of sigmoid function is like this, right? So we are done. Okay, this is this, and this is this, and this is, we already did this in previous slide, and this is this, and finally this is this. Okay, so you put these all together, okay, including the summation, and now it's this one. Now this one is this times this times this times this, including summation, right? You plug this in here and it multiplied by minus eta, and this finally a delta double j is like this. Okay, so that's why how we come up with this update rule for hidden node weight in the pseudocode. So the backpropagation is a widely used algorithm. Actually, the backpropagation is one of the most popular learning algorithm in the neural net. There has been many variations of backpropagation or gradient descent method in general. So I'm going to cover this the variations of gradient descent method in a different chapter, but here we're gonna study the one of the most common variations of backpropagation, is called momentum. So if you look at the pseudocode of backpropagation algorithm, then in step 4 we do have this formula. Okay, so the delta W n is eta learning rate times delta J times input. Okay, and this delta J depends on whether you update output node weight or hidden node weight. Okay, depending on that, you determine the value of this delta J. Okay, so that is original formula. And then if you use a momentum technique, you add another term like this. Okay, so alpha is constant. It's called momentum constant. And we have delta wji n minus 1. So this is the delta value in the previous step. This is delta value in current step. So you add a little bit of delta value from previous step. That is the basic idea of using momentum. So what it says here is we stick to the previous directions when updating weight values. We stick to the previous direction of updates. So it's like this: when you increase the weight values, okay, you keep increasing the weight values, okay, by adding positive values, okay, and then all of a sudden this delta value becomes very big, large negative values, and there is drastic change. It changes the direction drastically, right? And in machine learning in general, this is no good. Okay, it has very high variance in updating weight values, and probably this causes oscillation in the algorithm. So instead of that, we're going to update weight gradually, little by little. Okay, that's much better. So because of that, we add the value of a pre-delta in previous step. That's basic idea. Okay, so by doing so, we can avoid the drastic change in the value of weight. Okay. So here, nth iteration update depend on n minus one previous iteration value. Okay, and the alpha is constant between 0 and 1, and it's called the momentum constant. Okay. Actually, these days, as we use deep learning, this momentum is not a constant anymore. You have many other advanced techniques, and again, I'm gonna cover this topic in a different chapter of gradient descent. Okay. So again, the role of momentum here, this one is it's like the intuition here is you want to keep the ball rolling through small local minima in error surface. So suppose you have a ball and it's rolling in one direction, okay, and then you want to change the ball is going to change the direction in opposite way, okay, in opposite direction. Then what happens is the ball slows down and stops. Ball slows down and stops, and then in opposite direction it increases speed, right? So it doesn't change like it goes in one direction and all of a sudden it changes direction or go the other way. It doesn't work that way, right? So that's the intuition behind these momentums. When you change direction means when you update the weight, you change the plus sign of this delta value. It's kind of changing direction. Okay, so that's the intuition behind this momentum, like a ball rolling. Okay, so that's basic idea. And by using momentum, what it says here is if you have a small local minima, by using momentum, you are able to avoid this local minima problem by using momentum. The idea is like this. Suppose you have error surface has very small dent like this, okay? Small dent like this. You have a small dent like this, okay? Very small dent, okay? But it's small, but this is definitely local optima. So if you use momentum, you goes like this, okay? And then you go like this, and then if you use momentum, the next step, instead of staying here, you follow previous steps to end up here. Okay, so that way you can avoid this local optima. Okay, that's the basic idea. That's the advantage of using momentum. Let's take a look at the error surface of multi-layer network. Okay, using a sigmoid function or any nonlinear function. So if you remember the error surface of a perceptron network, it has only one global minimum, one global lowest point, okay? So if in a perceptron, if you find an answer, then that is guaranteed to be the best optimal answer, okay? But in a multi-layer network, okay, using a nonlinear activation function, because the activation function is non-linear, so if you visualize the error surface of multi-layer network, then it looks like something like this. Okay, it has many local minimum. Okay, it doesn't have one single global optimal minimum. It has many local minimum like this. Okay, so because of this, if you run a multi-layer network using nonlinear activation function, the answer you find, the answer you get is not guaranteed to be the optimal one. Okay, so you run this backpropagation algorithm and you get one answer. Okay, there is no guarantee that answer is the best one, optimal one. In the perceptron case, you train your network and get an answer, and that is guaranteed to be the optimal one. Okay, but in a multi-layer network, it is not the case anymore. Okay, so in multi-layer network, it suffers from a local optimal problem. So the answer you get is no guarantee to be the global optimal one. Okay, it may end up here. So if you look at this surface here, let's say you start from here, okay, and using a gradient descent backpropagation, probably you end up here. Okay. But if you start here, then you're using a backpropagation gradient, probably you end up here. This is the lowest point, right? So it depends on where you start. You may have a global optimal or local optimal. Okay, so that's the kind of a disadvantage of using multi-layer network. These are some remarks on backpropagation algorithm. So backpropagation is using a gradient descent. So because of that, it may cause some local minimum problems. Okay, as we have seen in previous slide. Okay, there is no guarantee that your answer is global or minimum. Okay, so in order to avoid the local minimum problem, you can add momentum, okay, but that doesn't. It may solve a little small dent of error surface, okay. But anyway, this is one method. Or you can use instead of stochastic gradient, stochastic backpropagation. Maybe you can use batch gradient descent. Or you can train the network with different initial weights using the same data. Okay, as I said in previous slide, it depends on where you start. You may end up in local minimum or end up in lowest global minimum. Okay, so you run the same network with different initial weight. That's another approach, maybe to avoid the local minimum problem. So again, because this gradient descent method is so popular, there are many advanced methods, many variations in many parts of gradient descent, including activation function, learning rate, momentum, regularization, etc. Okay, so many people are working on this, and I'm gonna talk about this in a different chapter. This shows an example of applying a backpropagation algorithm. Okay, and the task here is to predict whether a certain firm is to be bankruptcy or non-bankruptcy. So the data is collected between 1975 and 1986, and they use 5 data. Okay, and 5 financial ratios were calculated for each of the 5 aspects, and each of these which becomes the input for the network. Okay, these are the 5 inputs. Okay, X1 is working capital, total assets. Second variable is retained earnings, total assets, etc. So these 5 are the input to the network. Okay, so these are the network architecture, and because there are 5 input here, we have 5 input here. Input layer has 5 nodes, and we have one hidden layer which contains 5 hidden nodes, and we have one output node, output layer. Okay, and the class value is 0 or 1. 0 means bankrupt, 1 is non-bankrupt. Okay, so as a target value, we collect 129 companies, and so these were partitioned. These 129 companies were partitioned into two data sets. The first one is training data set, and second one is test data set. Training data set is used to train neural net. So the training data set is used to train this neural net. And the test data set is to evaluate the performance of neural net. Okay. So the training data has 74 companies, and 38 of them is bankruptcy, and 36 of them is non-bankruptcy. Okay, so using these 74 data, we train this neural net. Okay, and the performance is evaluated using the remaining test data. Okay. So at the end, this neural net was able to correctly predict 81.5% of bankruptcy and 82.1% of non-bankruptcy cases. So multi-layer network contains multiple hidden layers, right? And in this slide, we're gonna talk about what is the meaning of hidden layer in neural net. Okay. So what we see here is, let's say we have a neural net. Okay, one input layer, one output layer, and one hidden layer. And the input layer has eight input node, and we have 8 output node, and we have a 3 hidden node, right? And this network is called identity network. And what we do here is, when you give input like this, output should be like this. Okay, this is target value, this is input value, and these are same actually. So when you give input like this, output should be same, and when you have input like this, output is same. So input output should be same. So using this data set, we train this network. Okay, and then after 5,000 iterations, okay, this shows the final value of hidden node in this network. Okay, and then so then what is the meaning of these hidden node values? Okay, then if you look carefully, as in original input dimension is 8, it consists of 8 variables, 8 data, right? 8 values. And this data is somehow compressed into 3 dimensions, right? Remember, this output is generated only from hidden node. Okay, this one has no access to input layer, right? This output is generated only from hidden node data, right? So in that sense, entire input data is somehow compressed into 3 dimensions. Okay, because this output is generated only from hidden node, right? So somehow this original data is compressed into 3 dimensions, and then using this 3 dimensions, we are able to generate exactly same data. Okay, so original data is now compressed into 3 dimensions. So 8 dimension is compressed into 3 dimensions. So hidden node is actually a kind of compact representation of input data. Okay, that's the meaning of a hidden layer. And actually this is very, very important issue in deep learning. Okay, and this is the basis for feature learning, and also this is basis for autoencoder algorithm in deep learning. Okay, so this concept that hidden node is kind of compact representation of input data. It is a very important idea, and this is the basis for deep learning, especially in autoencoder and feature learning. So we have seen the basic concept of multi-layer network and backpropagation algorithm, and also how the you have seen how this backpropagation algorithm works. Okay, what are the weight update rules in backpropagation algorithm? Because of that, this neural net becomes a non-linear classifier and has been widely used in many applications. But even though in spite of its popularity in backpropagation, actually backpropagation has some problems. Okay, and because of these problems, and recently we don't use backpropagation anymore. We use something else like SVM or deep learning. So anyway, what are the problems of backpropagation? The first problem is vanishing gradient. By the way, I'm going to cover these issues here in a different chapter. Okay, called the deep learning chapter. So I'm going to give you a very short introduction here in this slide. So the first problem of backpropagation is vanishing gradient. Vanishing gradient means, so you have a neural net multi-layer, and you have, let's say, you have many hidden layers, okay, to represent a complex function, okay. I said, many layers, if you add many layers, then you are able to represent a very complex function, right? So to do that, let's say you add many layers. Then what happens is vanishing gradient means near the top, near the output layer, okay, then there are some changes in the weight values, okay, if you run backpropagation. But if you run backpropagation down here, like near the input layer, then actually nothing happens. The gradient becomes nearly zero. That means nothing happens, okay? So that's called the vanishing gradient. So in practice, if you have like, I don't know, maybe more than 5 layers, more than 5 hidden layers, actually there's nothing happens beyond 5 layers, 5 hidden layers, okay? So that's the problem of vanishing gradient. Basically, many layers doesn't make any difference, okay? Second problem is if you have many layers, then each layer is actually fully connected to each other. Each node is connected to every node in the next layer, right? So it is each node in the layer is fully connected to next layer. So because of that, we have too many parameters in the network. Okay, so because there are too many parameters, probably if you have many layers, the network suffers from overfitting. So the problem is because of this too many parameters and vanishing gradient, sometimes when you run backpropagation, people have to retrieve some important features, okay, from original data. So that's you have to retrieve features, by hand manually from original data. Okay, that's not easy. So that's another problem. So these are problems of backpropagation. So because of these, actually not many people use backpropagation anymore. We turn turn our attention to SVM or deep learning these days. So in order to solve these problems, we have another second breakthrough called the deep learning. This is proposed by Jeffrey Hinton. This is the person who proposed backpropagation in 1986. So this was his second major breakthrough in neural net. So deep learning was proposed in 2006, and this learning actually solves many of these problems by using these techniques: weight sharing, changing activation function, or learning layer by layer, or by using feature learning, etc. Okay. So again, we're going to learn this thing in the deep learning chapter.